this animation is going on in front of you for the last few minutes, and you have a Viva on laser also, right? I think there is an experiment. Some of you have given that Viva on that also. When you're in second semester, you have that laser experiment where you find out, use the transmission, grating, and so on. Okay. So there actually you are supposed to answer a lot of questions on laser if you choose that. Let me tell you that is one of the easiest Viva. But my experience is some of you I think I've already asked your Viva was not well prepared. It seems that the laser chapter was either not clear or you are a bit ignorant or you forgot. Okay, so I think neither of these cases are good. So what I will do is I'll actually explain laser to you, because let me tell you, if you are in branches like mechanical engineering or electrical engineering or even electronics and communication, okay, computers. So usually what happens is the engineers sometimes don't like what I say, but let me tell you, engineering is there, okay, it's a very specialized branches are there, but more or less engineering is a derivative of physics, okay. Somewhere there is maths, somewhere there is even chemistry, chemical engineering and all. We don't have that in our institute. But engineering is a derivative of physics, so physics plays a very important role, and that is the reason that in class 12 you must have physics, otherwise you cannot pursue engineering. Right? So please make sure that you understand these things, because if you are in mechanical laser cutters, if you are in computers, you have those CD drive, hard disk and all, okay, based on laser. If you are in communication, you are basically using optical fibers, but optical fibers actually, if you transmit the signal, you use lasers. Okay, if you are in electronics, okay, or electrical engineering, you basically make even those circuits and all by using laser cutting, because they have a very specific cutting property. Okay, if you're from any other field, remember that there will be one or the other application of lasers. So laser more or less is very much related, and you might definitely specialize in that. One more thing is, since we have time, I can just give you this basic idea that when you're going for your higher study, you might be doing your MTech, going for some kind of specialization. I think laser is a very good field to work on. There are a lot of upcoming startups where people work on lasers, so that is also an option for you. Okay, so it's everything. Okay, more or less. If you are working for a company and you are not really thinking about these things, but if you want to be your own boss, be an entrepreneur, you basically go with a startup, you should actually have the idea of the basic physics, very important. So that is also one more thing. Okay, some of you might be already thinking, because there are 2017-18 batches students also here, so you might be thinking about these things, okay, business and all. So you can always think about these things. Research, laser research is very much good in India. Okay, so this animation, okay, this animation somehow stopped, thak gaya ye bhi. So this animation is nothing but laser lighting system, and this basically works on whatever physics we are going to discuss now. And if you look into the hardware setup of a laser system, I think we all know about the helium neon laser. Okay, 6328 angstrom was the wavelength. This was also a common question which I asked. Okay, convert angstrom to nanometer. Okay, those things are important. But anyway, so we have got a helium neon laser where helium and neon are taken in some proportion, and a laser action is usually observed. And then we do have the anode and the cathode. Okay, so I'm not going to discuss this because this is actually not a part of your syllabus, but this is how exactly it looks like. Okay, when we look into the real things, okay, the practical application, we really feel inspired, and that's why I'm saying this. So laser usually, I think we already know it, okay, but I found that some of you don't know it. I was a bit strange. All of you know L is light. Okay, it started the animation. So all of you know that L is light, but then after that some of you got confused, and I did ask a very common question there, which may be a question later also. So laser basically stands for light amplification by stimulated emission of radiation. Okay, I'm just going to take it slow, because I think you should know these things, okay, apart from exams also. So amplification is okay, light is okay, and stimulated emission of radiation. So radiation is also fine, okay. So if you are having any kind of light coming out of a laser system, it might be a visible light, okay. Mostly, usually we see a red, green, blue laser and so on. We basically have the term stimulated. The question is, why do we call it stimulated? Okay, that is one of the questions that I asked, but I think none of you could answer it convincingly. Some of you did try. So this is important. So why it is called stimulated and not spontaneous? So these are some of the things that we are going to do. So in today's class, we are not going to look into any mathematical part. We are not going to derive Einstein's A and B coefficient, which is a part of your syllabus. Now we are going to discuss more about the theory and the terms, okay, so that everything becomes more or less clear. So laser characteristics, whenever someone asks you a question, I think this is one of the most simple answers that we should always have. Unidirectionality, okay, explaining one by one, okay, with some figures so that it becomes easy. So it will not basically scatter, it will be unidirectional. Can it scatter? Yes, it can scatter, but if it depends on for how much distance you are considering the directionality, okay. So it's not that you have a perfect laser. Please remember, there is no such thing as a perfectly monochromatic light, okay. It's very difficult, okay. Even the high-end monochromatic lights are actually not very monochromatic, okay. It's not very not purely monochromatic. So there is a term monochromaticity, that means the wavelength should be more or less very near to each other, okay. Theoretically single wavelength, but it's very difficult to get a monochromatic source. You have got those sources like argon and all, which we have as a monochromatic source, but then we don't use it in a lab because it's kind of costly, so we prefer using helium neon, sorry, not helium neon, sodium light, okay. So we use sodium light. So this explanation also I did, but we'll go to that further. High intensity, of course, because it is always said that you cannot look into a laser directly, because that might damage your pupil or the retina, right? Because it's very intense. It depends again how intense it is. Some lasers are not very intense. For example, the pointers that you use might not be very intense. But if you use a cutter, okay, which is basically used in, let's say from engineering point of view, mechanical engineering, okay. So if you are basically doing a very fine cutting using a laser light, it is very dangerous. It can cut metallic pieces. So imagine what will happen. It basically comes in touch with the human body. So you might have watched those movies like Matrix and all. You see that laser cutting, actually they show it as if it's a piece of cake, but it's obviously very risky, right? And then of course it's coherent, okay. So coherence means there will be a zero phase difference or constant phase difference, okay. So that is very important. When we say coherence, please remember this. Most of the people do say that there is no phase difference. Well, that is correct. There is a coherent source, but if there is a constant phase difference, that is also called coherent. So let me just give you some very simple figures on each of these properties. First is unidirectionality. So what happens is that what do you exactly understand by unidirectionality? So you have a normal light and you have a laser light. How do you exactly differentiate between the two? So what happens is conventional light sources will emit photons in all directions. You know, emission of light is nothing but all about emission of photons. So if you have a conventional light, okay, you have a light bulb in your room, you have a rod in your room, okay, or you have got a CFL bulb. In front of a CFL bulb, I think some of you might already know, there is something, there is a cover which is actually connected with it, okay. This is basically called a dispersion cover, okay. So it basically disperses the light, okay. So this is a disperser basically. So what happens is you can actually repair those CFL light, which was actually not possible with commonly all those old lights, okay. So what happened is inside there are some LED. In front of that we have a disperser. What is the function of the disperser? To diverse those photons or scatter these photons in all possible directions so that your room can be illuminated. So that is what is all direction means, okay. So in general, laser light definitely is different from this conventional light. So photons will be emitted only in one direction, at least theoretically. There might be slight deviation, okay. There are terms for it, okay, but not going into it. But there just might be slight deviation, but theoretically it will be only in one direction along the optic axis of the system. So in general, if you consider, I think you know about optic axis. You basically consider any kind of lens. You have the center, you draw a straight line from the center, okay. Then you basically call the optic axis. So basically whichever direction the light is coming out, it will keep on moving around that same direction. And then this is actually achieved by stimulated emission. And what do you mean by stimulated emission is something which is very important, which we are going to learn, and I'll make sure that all of you understand exactly what is stimulated emission. And this is what the reason why we actually call it as light amplification by stimulated emission of radiation. And then we have got the direction of optical resonating cavity. So resonance again is a very important term. Okay, so if you consider a laser like carbon dioxide laser, okay, which is a gas laser, very highly intense, used in cutting tools. So we have an optical resonating cavity. What happens is you have the laser signals bouncing between two mirrors. One of the mirror is 99% and one of the mirror is 100%. So what happens is because of that 1%, some of the rays will come out. Okay, and because of that to and fro bouncing, okay, continuous to and fro bouncing, it will come out with a very high intensity. The number of photons will come out at the same time. Okay, so that means that it will have a very high direction and it will actually be using this optical resonating cavity. Something which is very important is what happens in ordinary light. What happens in ordinary sources, photons usually get emitted by spontaneous emission. So when we actually consider something like a stimulated emission, you can actually have everything as per your own will. Okay, so you can actually control when the photon needs to be emitted, how many photon needs to be emitted, and so on. But when we say something is spontaneous, this is nothing but which comes to us naturally, like you're performing on the stage and everyone says that you are spontaneous. So that means you are natural in it, right? So this is something which happens with photons when we consider a general light or the ordinary source. Even the sunlight we consider is basically nothing but a source of spontaneous emission of light. Similarly, something like a CFL or the rod light or the whatever light source you are basically using, or the LED. So these are all spontaneous sources. So these are two differences between them, very much theoretical. I think you understand that. And then we will go for something which we call as the monochromaticity. So laser beam consists of photons, okay, but all of these photons, the photons are coming out, right? So if the photons are there, if you consider any kind of electromagnetic radiation, be it the visible light, be it the IR, be it the UV, and so on, all of these laser beam or whatever the laser beam you're considering, it will actually have photons, and these photons actually have wavelength associated with it, and these will actually have the same wavelength. So let's say if the wavelength is same, it will basically give out the same color or single color. So if you have a wavelength of around 500 or 550, I exactly forgot the range, okay, you will have one of the color in the visible range. So let's say your wavelength that is coming out is nothing but let's say we can consider 526 nanometer, right? So if you consider that, or 529 nanometer if you consider sodium light or something like that. So if you consider that, all of the photons will have the same wavelength coming out. But there is some difference always theoretically. So sometimes it does happen that there will be a difference. So that means there is no light source which can give you 100% monochromatic light. Okay. So there is no light source like that. There is always some or the other difference. Depends on how precisely the instrument is made. It can be very near, but might not be purely monochromatic. And if you consider to ordinary light sources, laser light is highly monochromatic. So you compare it with normal light, so obviously. So comparatively it is highly monochromatic. So there is something which is called line width, which is a measure of the monochromaticity. So that means how widely the wavelength is spread. Okay. So if you consider basically for an ordinary light, it is spread for 1000 angstroms. So before I proceed, please remember this is also a part of the syllabus. Okay, I'm not teaching you something extra. I'm just trying to give you some additional ideas. Okay, so that it becomes more clear and more interesting for you. Okay, so for ordinary light, what happens? You have the source, and this will actually be around 1000 angstrom. Okay, so angstrom, some of you could not answer during Viva. Is a bit sad about it, but it's 10 to the power minus 10 meter. Please don't get confused, okay? You should remember the units and the conversions. And then if you consider laser light, you can see that the width through which the wavelength is spread is only 10 angstrom. So for ordinary light, it's 2 orders greater, okay? 10 square greater. But for laser light, it is only 10 angstrom up to 10 to the power minus 4 angstrom. So when we consider something like 10 to the power minus 2, minus 3, minus 4 angstrom, this laser light is highly monochromatic. More or less we can say it's let's say argon light. Again, argon source, it will be very monochromatic. If you consider certain source, it will be basically near the vicinity of 10 angstrom, okay? Or even if you consider those laser light which we use as a pointer, okay, as a pointer in presentations and all, those are also nothing but near about 10 angstrom. So they are not very highly monochromatic. You cannot do a very good experiment or sensitive experiment, okay? So if you find out the let's say wavelength of light, okay, using the transmission grating. In transmission grating you usually see fringes, but if the light is not monochromatic you are going to see an overlap of these wavelengths, and as a result the fringes won't be very clear, and the answer that you get will be actually not accurate. Okay, there will be a widespread or wide variation of the wavelength that we have. Okay, next we have got high intensity. So how intense? So how do we actually measure intensity? So intensity is basically measured in terms of power, okay, in terms of power. So how much light is coming out per unit area or something like that, okay. So in that kind of measure we basically have the intensity as power. And then if we consider a very normal laser light, those handheld laser light systems and all, these will have intensity in the range of milliwatt. Please remember the values, because whenever you are writing down any kind of answer, even if you are not sure about the sentences, you are making some mistakes, but if you put the value correctly, you usually tend to score better. So I think this is preferable for all of you. So please remember the values first and then think about the answer, okay? You can put it somewhere, so it will always be preferable. Not only for physics, for any subject that you are studying, okay? We are technical people, so we will give our arguments in terms of values, okay? So if tomorrow anyone comes and tells me that this student's attendance is less, I will say that on this particular date he had exam, okay, so he could not attend. So I request you to allow him his attendance may be included for at least 2 days. So these are the values or the figures that I have, okay, because I know you have given your exam. So this gives a very good impression. You do any kind of writing, it's very important that you give values. So if you consider something like 10 to the power 7 watt, what does it mean? It means that the laser is of a very high power, a very high intensity. So very dangerous, okay. So but then look into this intensity of 1 milliwatt. So that means if you consider a light bulb which is actually scattered in all direction, you somehow manage to arrange all these photons to move only in one direction. That means 1 milliwatt of power will be 1000 times bright than the intensity of sun's light at the earth's surface. So you can understand this, okay, sun's light. But sun's light is like obviously at a particular region. It's not like you are considering the entire light and actually allowing it to fall on one place, or not that, but it's more intense than the sun's light and intensity at the earth's surface. So you can understand how intense it is, okay. And that's why if you consider something like a laser system, when we actually keep it on for a longer time, it gets heated up. So if you are really thinking about doing any kind of business or startup in lasers, you basically need to consider these factors. The cooling factor, that is very important. A normal CPU which runs on a processor needs a cooler. So imagine a laser which will actually use that much of power. For example, let's say this is actually very upcoming technology, okay. We are usually not using it much in India. In the south west it is used, okay. So what happens is you have got those laser lighting which actually are used as billboards for advertising. So you basically have a system in the ground and you are projecting a laser, and you are somehow projecting, I don't know the exact technology, you are somehow projecting it on the sky. So you don't need any space for advertising, okay. You can directly use the sky as a space for advertising. So imagine the depth of the idea, okay. It can be used, okay, anywhere and everywhere. But there those laser systems definitely needs to be maintained in a specialized enclosure and all those things. So fan system and all these things are very important. So you can imagine how intense these are. Take a normal torchlight and just switch it on and put it on the sky, and you are not going to observe anything. Okay, so let's go for the last topic, which is coherence, one of the properties. Okay, so what happens is the important term here is in phase. Okay, is in phase. So the light waves which are basically emitted by the light source will be in phase, and it will be of same frequency. Okay, so the frequency will remain the same and it will be in phase. Okay, so I hope all of us remember what is the relation between frequency and wavelength. It is inversely proportional. So if we consider the wavelength doesn't change, so obviously the frequency also doesn't change. Okay, so both of them are interrelated, and as a result we can say it will be highly coherent. So see, sometimes what happens is when we listen to these terms asked in Viva or in general, we get a bit scared. But see, if you know the definition, these things are simple. Okay, these are all scientific terms which are used, but the meaning is not difficult. So there is something which is called coherence length. So that means for how much distance the medium will actually remain coherent, okay, up to which the two light waves emitted will be in phase with each other. So you basically have a laser, light waves are coming out of it, photons are coming out of it. Up to how much length it will be in phase. So you see there might always be slight difference. So if I draw something here, it is definitely going not going to be perfect. That's for sure. Because see, I can say okay these two are in phase, but do you really think these are in phase? Actually not, because if you keep on pronouncing it in forward, okay, if you keep on moving it forward, you will see that slowly but surely there will be a difference which will be coming out between the maxima of these two. So that means there will be a phase difference which will be included as we go for a longer distance. So coherence length is very important. So if you consider something like coherence length, and as I give you that example that you can have a advertisement on the sky, okay, that should actually have a very good coherence length, a longer coherence length. If you have a shorter coherence length, by the time it reaches, the signal gets lost, okay, you don't get a very intense beam to actually show up. So that is what is coherence length is all about. So we do have a relation, but that's not in a syllabus, so we are not going into that. So let's go for the next one. So this is something which is very important, and that is why we are actually studying the laser, and this is something which is important for us because we are studying the technical part. So why there is production of laser? So the production of laser is a consequence of the interaction of radiation with matter. Now this is altogether a different topic, okay, interaction of radiation of matter. So what happens is, what happens when radiation interact with matter? So this radiation might be, let's say, visible light, it might be UV radiation, IR radiation, and so on. So what happens exactly to the system? So if you have a atomic system, let's say you've got a hydrogen atom, or you have got a lithium atom or something heavy, let's say uranium and so on, okay, and then you have got some kind of radiation falling on it. What happens? Okay, so this is something which is altogether a different vast topic, but we are going to look into it partially. I have a lecture on this interaction of radiation with matter on YouTube. I'll just share it with you if you are interested. But this was actually in MSc course, part of MSc course. So there are three methods by which radiation interacts with matter. So there are different ways of categorizing it, okay, but in terms of laser, I think it is best to keep it in this way. There are three methods of interaction of radiation with matter, and what happens is that when radiation interacts with matter, there is something which we call as the induced absorption, okay, and then we can actually have a spontaneous emission, and then we are going to have something which is called the stimulated emission, important for laser action. So before I really go into what is induced absorption and all, let me just tell you this basic term. Induced means you are actually forcing it to absorb, okay, forcing it to absorb, or in general you are allowing something to fall on it and it absorbs, okay. So might be you have got a piece of sponge, you are putting some water, it particularly gets absorbed, okay. So there is an induced absorption. You put the water, then only it gets absorbed. Something which is spontaneous means it happens on its own, okay, doesn't need any kind of external stimulant, okay, and stimulated emission is it needs an external stimulant, okay. So this is basically the difference between these three. I think this is very simple, a very schooling chapter, because these things more or less will be easy for you, okay. So I will be uploading the notes, okay, after this class, or maybe after the next class, once I want to finish the topic in a good way. There I have written every sentence on induced absorption. Here I have not included. Too many sentences in a PowerPoint presentation is actually not a very good idea. So let me just explain this to you verbally so that you understand. So even if you don't have the notes, definitely you can write it down, okay. So what happens is, in induced absorption, you basically have got two energy level, and then that's E1 and E2, and these two energy levels will have some atoms, okay. So it might be N1 and N2. So there will be some atoms at N1 and N2. Now you know in nature what happens is everyone wants to be in its ground state. So everyone wants to be in its stable state. You might be very happy, you might be moving around, okay, very excited the whole day, but you cannot remain in that state forever. You basically will come down, calm yourself and go to sleep, okay. So that is basically the ground state for us. So generally what happens is that is what dictates nature. Everything wants to be in its ground state. So we have got the energy level E1 and we have got the number of atoms N1 there. And if you consider a natural process, the number of atoms at the ground state will definitely be maximum. But then what happens is you can actually allow some energy to fall on it, and that energy might be nothing but the incident photon. So what can this incident photon be? So again, it's a photon. Not necessarily it should be directional, not necessarily it should be laser. it has to be photon. So you know sometimes what happens is you get the process of luminescence, okay, or you get those watches, okay, which actually radiates at night, okay. So you can actually look into the dial of the watch at night because it has got radium, which is actually a chemiluminescent material. So that is basically called a chemical luminescence, or in short chemiluminescence. So that is an example of induced absorption. So what happens is you have the natural light falling on that radium, and then basically that absorbs, and then when it relaxes it emits the light. So that is what is happening there, okay. So here also we are talking about induced absorption. So we basically have a photon falling on the system, and this will have two energy levels, and then as soon as the photon falls on one of the atom, it will basically go and jump to the upper energy level, okay. Now it jumps to the upper energy level. That means it has absorbed some energy and it has gone to the upper energy level. It will definitely absorb the energy and go to the upper energy level because we have to take care of absorption of conservation of energy, right? And then it goes to the excited state. Please remember, in exam, don't get confused between induced absorption and spontaneous emission. In induced absorption, I am not talking about emission here, okay? We are only talking about absorption. So before it was in the ground state, and after it got to the excited state. That's all. That is induced absorption. Don't explain anything else. Anything else is not asked, okay? So if the question is that. So I think this is very simple, induced absorption. And then what happens is we have got the atom and the photon which is incoming, okay? It can be from an external source. And then the atom goes into the excited state, and that's why we use a star. So I hope you remember a bit of nuclear physics from your class 12. Whenever you are talking about a nuclear fission reaction, you talk about uranium and you put a star there. That means that star signifies something which is unstable in nature. So if you have got a neutron hitting a uranium-235, you get uranium-236. Uranium-236 is written as an asterisk because that is unstable. It is going to come to the stable state. So here also atom asterisk, actually it's an excited state, representing an excited state, but in general we can connect it with that. This is more or less unstable. It cannot remain there forever, okay. So in general, if you consider the relation, it will be A, which is the atom, plus h nu. So any photon will actually have energy of h nu or hc divided by lambda, okay. Please remember those relations, important for numerical problems. And then it will actually have the excited atom, which is nothing but A star. So next is spontaneous emission, okay. I'm covering a lot of things. We will probably take a break for some time after we finish the emission part. And then spontaneous emission, we have got E2 at the upper energy level, E1 at the lower energy level, but now the atom is considered to be the excited state. The question is, you will ask that why it is in the excited state. It might be for a number of reasons. Might be it is the process after the induced absorption. So right now, in order to understand theoretically, we just say that the atom is in the excited state. Why might be a case which will be understood later. So we have it in the excited state, and then it cannot remain there forever, okay, because it is at a higher energy state. It will actually want to come to the ground state. So it will radiate, or it will start coming from E2 to E1. And this happens spontaneously. That means it happens on its own, and then it finally comes in the ground and sits there. So this is basically called a spontaneous emission. The question is, why emission? Because if it was at a higher energy state, it was having some value of energy, but E1 is lesser. So this has come from higher energy to a lower energy. So that means in order for conservation of energy, some of the energy must be given out, and that energy is given out in the form of photon. This is what happens in that case of that watch, okay, the radium watch you can actually see at night in dark, okay. So this is what is happening. So the emitted photons are actually given out, okay. The intensity is less in that watch example. Another example, the intensity might be very high. But please remember, these two are not responsible for laser action. We will soon come to it, why this is not responsible for laser action. So we have the atom in the excited state, that's why there is a star. And then we have the final output as atom coming to the ground state and be at rest. And then the photon will be actually emitted. So that means A star is equal to A plus H nu. So this is again the same relation. But you have to understand the importance of putting a star on the left hand side and the right hand side, okay. So I think this is more or less clear to all of you. And finally we come to what we call as the stimulated emission. So what happens is, I have a atom at the excited energy level. Eventually it will come down, but that will come down on its own. What if I can control it. So what if I can have a photon emitted, okay, when the atom goes from the excited state to the ground state on my own will. That will actually be something which will be helpful for laser action. Right now let's understand what is stimulated emission, then later on we will understand that how, okay. So the photon is incident and there is a kind of interaction. Let me tell you this, okay, this is actually something which usually is not explained in the class. What kind of interaction this incident photon has with the atom here is still unknown, okay. This is something which is still a question, okay. People are not really sure, because what happens is after this photon passes through, this atom will come down. So if this atom come down, we are expecting that some energy is actually given out. So this is the energy, let's say, emitted photon. But what happens to the incident photon? This will also come out without losing any kind of energy. So that means you have one incident photon and the output is two photons coming out. One is the de-excited, the photon coming out because of the de-excitation, and another is the original photon that went in. Both of them are coming out together. So that means we have got a multiplication or division of photons. Okay, so laser action actually is based on this, that if somehow we can actually excite a atom, okay, and then allow other photons to interact, and many photons or many atoms comes down to the ground state at the same time, it will emit a number of photons, okay, and then that will actually result in something which we call as the laser action. Okay, so we are going to look into that, but before that let me just tell you why we consider that these two photons are more or less having the same wavelength. So you see there is an energy difference between E1 and E2. So if we consider E2 minus E1, the energy is nothing but h nu, right? So we already know it. Okay, so we have got h nu. So h nu means hc by lambda. hc by lambda means lambda is fixed for this particular energy gap, hc divided by lambda, because you know that the energy gap will be constant. Okay, you don't have a dynamic energy system, these energy gaps will remain fixed. So h is a constant, Planck's constant, c is the speed of light, and of course definitely lambda should be fixed so that the energy gap difference doesn't change, and obviously it cannot change. Okay, so that means lambda is fixed. So if we have a photon which is actually having an energy same as the energy gap between these two, this will actually help to trigger this photon at the excited state to come at the ground state. So if both of them has got the same wavelength, okay, from this particular relation, that means they are more or less coherent. Okay, sorry, not coherent, monochromatic. Okay, so that is basically what is monochromaticity is all about. So we are actually having a monochromatic source of light coming out. So you can have any kind of light. Okay, you can have a visible light, but doesn't mean that all the wavelengths of visible light is composed of a number of wavelengths. It doesn't mean that all the wavelengths which actually trigger the effect. Okay, there will be only certain wavelength that will trigger the effect. Okay, but we will see what exactly do we use in an example of this. Okay, so after this we are actually going to start with condition for laser action. This is also a lot of theory. So let's take a break. Okay, let's take a break for